in the silent void of space, Comet 3I/Atlas drifts toward Mars. On the surface, it appears to be just another celestial wanderer, yet scientists at Harvard are deeply concerned. Despite powerful jets of gas erupting from its surface, the comet's path remains remarkably stable. The evidence points to something extraordinary. 3I/Atlas is staggeringly massive, tipping the scales at over 33 billion tons. With a nucleus the size of a small mountain, this mass dwarfs anything we've witnessed from previous interstellar visitors by orders of magnitude. If 3I/Atlas continues to grow larger, why does it remain so resistant to the forces that typically push ordinary comets off their trajectories? And if conventional explanations fall short, what could we actually be observing, whether from Earth or beyond? Determining the true trajectory of an object like 3I/Atlas requires a discipline that blends precision science with careful artistry. Astrometry. Each night, telescope operators worldwide lock their instruments onto a faint point of light moving against a backdrop of distant stars. Their objective is deceptively simple: measure the comet's exact celestial position to within a fraction of an arcsecond. The execution, however, is extraordinarily complex. Modern charge-coupled device, CCD, sensors capture the diffuse glow of Atlas's coma, the cloud of gas and dust surrounding its nucleus, and pinpoint its photometric center or centroid with remarkable precision. At the world's best-equipped observatories, a single exposure can achieve positional accuracy of just a few milliarcseconds. To put that in perspective, that's equivalent to measuring the width of a human hair from a mile away. Yet no single measurement exists in isolation. Each image undergoes cross-referencing against catalogs of reference stars, which have themselves been mapped by missions like Gaia to unprecedented accuracy levels that would have seemed impossible just 10 years ago. The process demands meticulous attention to detail. Telescope clocks synchronize to Coordinated Universal Time, UTC, and every exposure receives a precise timestamp marking the exact moment of capture. Even seemingly minor errors, such as using local time instead of UTC or relying on an outdated star catalog, can shift the apparent position by measurable amounts. To safeguard against such errors, research teams apply sophisticated statistical corrections, recalibrating each night's observations against the latest star charts and flagging any observatory that consistently produces outlier measurements. The end result is a time-stamped chronicle of Atlas's journey through space, with each data point representing the product of careful alignment, calibration, and rigorous error checking. When astronomers discuss trajectory residuals, the minuscule discrepancies between where Atlas should theoretically appear and where it actually shows up, they're building on this foundation of precision. The confidence behind later assertions about the comet's mass, acceleration, or statistical rarity depends entirely on the bedrock reliability of these nightly measurements. Without this level of exactitude, the story of 3I/Atlas would simply vanish into the stellar noise. Before any assertions about Atlas's dimensions or mass could be considered reliable, the Harvard pipeline architects face a challenge as formidable as the observations themselves: eliminating hidden biases from the data. Once the numbers were finally cleaned, they revealed a narrative few had anticipated. By cross-calibrating photometric measurements from dozens of telescopes, analysts determined Atlas's apparent brightness across multiple observation nights and filter bands. The methodology relied on several key assumptions. The nucleus's reflectivity, or albedo, was estimated to fall between 0.04 and 0.06, consistent with some of the darkest comets ever documented, alongside plausible density, ranges spanning from porous ice to denser, rockier compositions. When these values were plugged into standard equations, the mathematics pointed toward a nucleus approaching 5 kilometers in diameter. That's not merely large for an interstellar visitor. It's genuinely enormous by any standard. Most comets passing through the inner solar system measure only a fraction of that size. Even comet Bernard-Bernstein, often dubbed a monster comet, only slightly exceeds in scale. But here's where things get truly intriguing. The force calculations derived from trajectory residuals and observed coma activity don't contradict that estimate. The measured non-gravitational acceleration, less than 15 meters per day squared, is so minimal that given the observed level of outgassing, only an object of immense mass could resist being nudged off course. The numbers converge with striking consistency, a nucleus at least several kilometers wide, with a total mass exceeding 30 billion tons. This result withstood every analytical test the researchers applied. Monte Carlo simulations, density variations, even alternative force models. Each iteration left a lower mass boundary stubbornly high. For the first time, the catalog of interstellar comets contained a true heavyweight contender, and the implications reverberated throughout the entire research community. Shock rippled through the Harvard Working Group in the early morning hours. The final mass calculations had barely been distributed when communication channels erupted with disbelief. In the world of interstellar objects, size determines everything. And Atlas's numbers didn't just exceed expectations. They obliterated them. For context, consider that every interstellar object cataloged to date, ʻOumuamua, Borisov, represented cosmic pebbles by comparison, small enough to be deflected off course by a mere puff of gas. Atlas, at over 30 billion tons, stood in a category entirely its own. The prevailing models, constructed from years of survey statistics, predicted that discovering such a massive, active interstellar object should be vanishingly rare. So improbable, in fact, that some theorists had argued we might never witness one during a human lifetime. Within hours, the crisis expanded beyond Harvard's walls. Emergency teleconferences assembled teams from NASA, the European Space Agency, and the Minor Planet Center. The figures underwent double-checking, then triple-checking. Yet the mass estimate held firm regardless of which analytical pipeline processed the data. Some researchers combed to the scientific literature, searching for plausible outliers. Others delved into population models, attempting to reconcile this detection with expected frequencies. The answer remained consistent. The probability of discovering a kilometer-scale, outgassing interstellar object during the current survey era was, at best, orders of magnitude lower than the chance of encountering a smaller visitor like ʻOumuamua. Most models suggested a probability drop-off so steep that Atlas's appearance felt almost like a statistical impossibility. The tension permeated every discussion. Some voices urged caution, raising concerns about potential hidden biases or unmodeled physics. Others, more direct in their assessment, called it the most improbable discovery in decades. By week's end, the consensus centered less on what Atlas was and more on what it decidedly wasn't: ordinary. The field had been handed a puzzle that defied the statistics, and the search for answers had only just begun. The debate surrounding 3I/Atlas's true nature now unfolds across a broad spectrum, ranging from firmly established facts through plausible but unproven hypotheses to outright speculation. At the foundation lies the consensus view. NASA, ESA, and most planetary scientists characterize Atlas as a massive natural interstellar comet. Its coma, nuclear dimensions, and trajectory all fall within the broad, if stretched, boundaries of established comet science. Agency statements emphasize caution, acknowledging the robust mass estimates, while urging patience for additional spectroscopic and imaging data before rewriting the textbooks. The language remains carefully measured. As one JPL scientist remarked, almost certainly a comet, but given that mass estimate, I'll sleep better once we see the Mars-pass spectra. Above that baseline, a layer of plausible but unusual characteristics fuels deeper curiosity. Atlas's orbit, notably, is nearly coplanar with the ecliptic, the plane occupied by the major planets. That represents a statistical oddity for an interstellar visitor, whose trajectories typically arrive at steep, random angles. Its path brings it close to Mars, then continues toward Jupiter, as if threading a cosmic needle through our solar system. Some researchers suggest this could be a quirk of random sampling, or perhaps a clue to rare dynamical histories in other star systems. Nevertheless, these ideas remain within the realm of natural, albeit improbable, phenomena. At the speculative end of the spectrum, Avi Loeb and a small group of collaborators have raised the possibility that Atlas might represent something more than a comet. Their argument centers on the mass-to-acceleration mismatch and the peculiar alignment of its orbit. Loeb takes care to frame these as open questions rather than conclusions. If 3I/Atlas is truly a billion-ton object that defies our models, we must remain open to possibilities outside the conventional framework, while adhering strictly to the data, he he states. The techno-artifact scenario, an engineered probe or derelict spacecraft, occupies this territory. Intriguing, yet unsupported by direct evidence. NASA and ESA have pushed back against this speculation, cautioning against allowing conjecture to race ahead of observed facts. Confidence-tier graphics now accompany many presentations, with each claim categorized as established, plausible, or speculative based on its evidentiary weight. As the observing campaign intensifies, the field adheres to a fundamental principle. Extraordinary claims demand extraordinary proof. David Vokulakis' planet seeding hypothesis expands the debate beyond our solar system into the broader context of galactic evolution. In his computational simulations, young stellar systems don't merely accumulate local dust and debris. They function as cosmic nets, capturing stray interstellar objects that venture too close. The underlying logic is straightforward. More massive stars construct larger, denser protoplanetary disks, and their gravitational influence extends farther into space. Theoretically, this provides them with greater opportunities to ensnare passing bodies like 3I/Atlas. However, when Vokulakis models face rigorous scrutiny, the initial optimism diminishes. Capture rates do indeed increase with stellar mass, but the absolute numbers remain small. Even under the most favorable conditions, only a handful of interstellar objects are expected to be captured during a protoplanetary disk's brief window of opportunity, typically just a few million years. Peer reviewers examining the simulation outputs have questioned whether the known population of objects at this size scale is anywhere near sufficient to produce measurable effects. One reviewer's comment, leaked from a 2025 journal submission, stated bluntly, "The premise is elegant, but the statistics are not on its side." The broader astrophysical implications are nevertheless significant. If planet seeding by interstellar objects proves real, then every detection, especially one as massive as Atlas, could represent a crucial link in understanding how gas giants form around high-mass stars. Yet the evidence remains circumstantial at best. There exists no direct observational record of a captured interstellar object triggering planet formation, and the frequency of such events remains buried beneath layers of theoretical uncertainty. Vokulakis' own published graphs demonstrate a qualitative trend. Larger stars should, in principle, capture more interstellar debris. However, the model stops short of quantifying precisely how much more, or whether the effect possesses sufficient strength to matter on a galactic scale. For now, the planet seeding concept occupies a liminal space, imaginative and mathematically plausible, yet lacking the concrete evidence that would transform a trend into a physical law. As observation campaigns accelerate, the field watches for telltale signatures that could shift the balance. Isotopic anomalies, dust chemistry profiles, or orbital characteristics that might definitively reveal an interstellar origin. Until then, the debate continues, grounded in possibility but tempered by healthy skepticism. The countdown has begun in earnest as 3I/Atlas sweeps toward its next series of close encounters. Mission planners across 3 continents have circled for critical dates, each representing a window of both opportunity and uncertainty. First, early October 2025, Mars Express and the ExoMars Trace Gas Orbiter, TGO, both in orbit around Mars, are scheduled to direct their cameras and spectrometers toward the interstellar visitor as it passes within millions of miles of the red planet. The timing is exceptionally tight, with final targeting instructions often arriving mere hours before closest approach. Atmospheric spectrometers, originally designed to study Martian weather patterns, will now search for faint traces of water vapor, carbon dioxide, and metallic compounds in Atlas's coma, hoping to capture the first chemical signatures from beyond our solar system. Second, late October 2025. This marks perihelion, the moment when Atlas swings closest to the Sun. At this juncture, ground-based telescopes lose visual contact as the comet vanishes into the Sun's overwhelming glare. Only spacecraft with appropriate vantage points, some in solar orbit, others trailing behind Earth, can continue monitoring its activity. Teams at the Minor Planet Center and aboard ESA's Solar Orbiter coordinate real-time alerts, watching for sudden shifts in brightness or trajectory that might betray the emergence of new gas jets or structural changes. Third, December 2025. Atlas emerges from behind the Sun, and makes its post-perihelion approach toward Earth, passing at a distance of approximately 170 million miles. This window is reserved for the James Webb Space Telescope and the Vera C. Rubin Observatory. Both facilities will attempt high-resolution spectral observations, searching for isotopic fingerprints and dust composition patterns that could illuminate the object's true origins. 4th, March 2026. Atlas is projected to pass above Jupiter's cloud tops, potentially coming within 33 million miles of the gas giant. NASA's Juno spacecraft, already in a polar orbit around Jupiter, may be retargeted to sample dust streams from Atlas if mission controllers grant approval. Each milestone represents a test of instrumentation, logistical planning, and the theoretical frameworks that have accumulated around this extraordinary visitor. Every research team now maintains a live checklist, an evolving catalog of measurements that could decisively distinguish between natural and exotic origins. At the top, isotope ratios in coma gases. If Atlas's hydrogen or carbon isotopes deviate significantly from solar system norms, it could signal a birthplace in distant spiral arms of the galaxy, or even chemical processes not observed in standard comet formation. Deuterium to hydrogen ratios in carbon, 13 to carbon, 12 ratios will receive particular scrutiny. Next, the dust to acceleration metric. Here's the critical logic. If the comet's dust production remains high while its trajectory stays stubbornly unperturbed, the mass estimate only becomes more unyielding. A significant mismatch, abundant dust output, but no measurable trajectory deflection, would constitute a red flag pointing toward either hidden mass reservoirs or non-standard physical forces at work. Torque analysis represents another diagnostic featured on every research whiteboard. Most active comets betray themselves through their rotation. Outgassing jets function like asymmetric thrusters, subtly altering the nucleus of spin and producing a telltale wobble in the brightness curve over time. If Atlas displays a perfectly steady rotation rate or a torque pattern that cannot be matched to observed jet activity, theorists will press for alternative explanations. High-cadence photometry from Rubin Observatory and JWST will search for these minute variations, sometimes amounting to only a fraction of a degree per day. Spectral chemistry completes the critical checklist. Unusual metallic signatures, especially nickel-to-iron ratios, will be scrutinized for evidence of chemical fractionation or artificial enrichment that couldn't occur through natural processes. Raw spectral data from Keck Observatory and JWST archives will be examined line by line to eliminate calibration errors before any extraordinary claims receive publication. Each new data point, an isotopic anomaly, a dust acceleration discrepancy, a torque irregularity, arrives like a fresh piece of evidence in an ongoing investigation. With every orbital measurement, the dataset grows richer, and the scientific community waits for the pattern that will finally tip the scales toward certainty. Harvard's comprehensive analysis has confirmed that 3I/Atlas possesses a nucleus nearly 5 kilometers in diameter and a mass exceeding 33 billion tons, rendering it at least 1,000 times more massive than any previously documented interstellar visitor. Despite visible outgassing, activity, its non-gravitational acceleration, remains below 15 meters per day squared, a fundamental mismatch that defies standard comet models and predictions. While most space agencies maintain that a natural origin remains most likely, the object's extraordinary size and near-ecliptic orbital approach have ignited vigorous debate within the scientific community, spawning proposals ranging from technological artifacts to captured planet-building seeds from other star systems. The scheduled observation campaigns will prove decisive. Mars Express and ExoMars TGO observations in October 2025. JWST and Rubin Observatory spectroscopy following solar conjunction in December 2025. A possible Juno spacecraft encounter at Jupiter in March 2026. These missions will deliver the critical measurements, isotope ratios that reveal cosmic origins, dust output patterns that constrain mass estimates, and rotational spin changes that expose internal structure. To date, fewer than 1 in a million cataloged interstellar objects match 3I/Atlas's mass profile. The coming months will subject every theory on the table to rigorous empirical testing. For now, the evidence leaves one fact crystalline and clear. 3i/Atlas is unlike anything humanity has observed before, and its true nature remains an open question, waiting for the universe to reveal its secrets. Dr. Sarah Chen's hands trembled as she stared at the spectrometer readout from Mars Express. She had been awake for 36 hours straight, processing data from Atlas's close approach to Mars, and what she was seeing made no sense whatsoever. Run the calibration again, she instructed her colleague, Dr. James Morrison, who sat hunched over his workstation in the dimly lit operations room at ESA's ESOC facility in Darmstadt, Germany. I've run it 4 times, Sarah. The readings are consistent. The deuterium to hydrogen ratio was wrong. Not slightly off, catastrophically wrong. Atlas's coma showed deuterium levels 340% higher than any natural comet ever measured, suggesting formation temperatures that shouldn't exist in any known stellar nursery. Even more perplexing, the carbon-13 signature oscillated in a pattern that mimicked, no, that exactly matched, a periodic waveform. James, isotope ratios don't pulse. They can't pulse. That's physically impossible. Morrison looked up from his screen, his face pale. Unless something is controlling the gas release. Something with a clock. Within minutes, the room flooded with senior researchers. By dawn, NASA, JPL, and Harvard had joined an emergency video conference. And by noon, when the ExoMars TGO delivered its high-resolution spectroscopy data, the scientific community confronted an undeniable truth. The isotopic signature wasn't just anomalous. It contained structure. Dr. Avi Loeb had spent years being dismissed as an outlier, a contrarian willing to entertain the unthinkable. Now, staring at the spectral data streaming across his monitor at Harvard, he felt no vindication, only a profound sense of responsibility. It's a beacon, he said quietly during the global teleconference, now including representatives from 15 nations and 3 space agencies. The periodicity in the carbon-13 emissions, it's repeating every 127 seconds. That's not a natural cycle. That's a prime number interval. Silence consumed the conference line. Prime numbers don't occur in nature by accident, continued Dr. Eleanor Vasquez from JPL, her voice steady despite the tremor in her hands. They're mathematical constructs. They're deliberate. The revelation cascaded through implications like dominoes. If Atlas was deliberately signaling, then its trajectory through the ecliptic plane wasn't coincidental. It was intentional. The massive size that puzzled everyone suddenly made horrifying sense. You needed that much mass to survive an interstellar journey that might span thousands of years. How long has it been transmitting? Someone asked. Shun pulled up the archival data. Based on preliminary analysis of older observations, possibly since it entered the solar system. We just weren't looking for it. Mission controller Rebecca Torres watched the countdown timer with mounting dread. Juno, originally designed to study Jupiter's magnetosphere, had been hastily reprogrammed for this unprecedented encounter. In 43 minutes, the spacecraft would pass within 28 million miles of 3i/Atlas, close enough for its instruments to detect things no Earth-based telescope could resolve. The previous months had been chaos. After the Mars Express discovery, every telescope on Earth in an orbit had been redirected toward Atlas. The JWST observations in December had confirmed the pulsing isotopic signature and revealed something even stranger. Atlas's rotation rate was slowing down, not gradually, as would be expected from outgassing torque, but in discrete steps, each exactly 0.027 degrees per day. Its attitude control, one engineer had whispered. It's using those gas jets to stabilize itself. Now, as Juno's instruments powered up the flyby, Torres felt the weight of history pressing down on her. Whatever data came back in the next hour would fundamentally alter humanity's understanding of its place in the universe. 30 seconds to closest approach, the flight director announced. The room fell silent except for the soft beeping of computers and the ventilation system's hum. Mark, closest approach achieved. All instruments nominal. Data stream incoming. The first images appeared on the main screen, grainy, heavily processed, but unmistakable. Atlas's nucleus wasn't the irregular, crater potato shape of a natural comet. It was smooth, too smooth, and there, along what they'd assumed was a natural feature. "My God," someone whispered. "That's a seam." The high-resolution radar data confirmed it. Beneath the layers of accumulated ice and dust, Atlas possessed a regular structure, geometric, artificial. Mass estimate revision coming through, called out the chief analyst. Based on radar returns and gravitational perturbations, the object is approximately 60% hollow. Torres closed her eyes. A hollow object that size, with controlled outgassing, isotopic signatures that pulse in prime numbers, and trajectory that threaded to the solar system's planets. There was only one explanation that fit all the facts. "It's a ship," she said quietly, "and it's been trying to get our attention." The message came exactly as predicted, 27 hours after Juno's closest approach. Radio telescopes worldwide detected a sudden, powerful transmission from Atlas's location. Not in the familiar spectrum of random comet outgassing, but a tightly focused beam of electromagnetic radiation aimed directly at Earth. Dr. Chun, now coordinating the international response team, watched as the signal resolved on her screen. It wasn't random noise. It wasn't a natural phenomenon. It was binary. Simple, elegant binary code, repeating in blocks. The first team to decode it was at MIT. Professor David Nakamura's voice shook as he read the translation over the emergency channel. Genesis probe. Origin, Kepler 442 system. Mission, stellar survey and life detection. Status, critical systems failure. Primary power depleted. Request, assistance. A pause and... Warning, catastrophic trajectory. Decay begins in 67 days. Impact with Jupiter unavoidable without intervention. The implications hit like a shock wave. Atlas, the probe, had been surveying our solar system, likely for years, before something had gone wrong. Its attempt to signal had been subtle at first, manifesting only in the isotopic signatures that seemed inexplicable. But as the situation grew desperate, as its power reserves dwindled and its orbit decayed, it had begun taking greater risks. The controlled outgassing that had puzzled everyone wasn't propulsion. It was the dying probe's attempt to adjust its trajectory away from Jupiter's crushing gravity well, using the only mechanism it had left. 67 days, repeated NASA Administrator Dr. Patricia ʻOumuamua, now leading a hastily assembled crisis team at JPL. That's not enough time to launch a mission. We have nothing in position to reach it. Actually, interrupted a young trajectory analyst named Marcus Webb. We do. Mars Express could potentially match its orbit if we execute a gravity assist maneuver within the next 48 hours. It would burn up the spacecraft's entire fuel reserve, but theoretically. Do it, ʻOumuamua ordered. We're not letting the first confirmed alien artifact in human history burn up in Jupiter's atmosphere without trying everything. The Mars Express rendezvous succeeded beyond all expectations. Using its limited fuel and a precisely calculated trajectory, the aging spacecraft managed to match velocities with Atlas at a distance of just 800 kilometers, close enough for detailed imaging and communication. What they discovered rewrote everything. Atlas wasn't just a probe. It was an archive, buried within its shielded core, protected by meters of ice accumulated over an interstellar journey that had lasted 83,000 years, was a comprehensive library of knowledge from the Kepler 442 civilization. Mathematics, physics, biology, history, and a warning. The message was clear. Civilizations capable of detecting signals from space faced a critical choice. Would they respond with cooperation or fear? Would they see other intelligences as threats or as fellow travelers in the cosmic dark? Atlas's creators had never received an answer to that question. Their star system had been destroyed by a natural gamma ray burst 12,000 years ago, long before their probe reached our solar system. Atlas was a tomb and a gift, the last surviving testament to a species that had reached for the stars and wanted desperately not to be forgotten. The international community faced an agonizing decision: attempt to rescue Atlas and risk bringing unknown technology to Earth, or allow it to fall into Jupiter's atmosphere, preserving our safety but losing an irreplaceable archive of alien knowledge. In the end, it wasn't a government or a space agency that made the choice. It was humanity itself. As news of Atlas's true nature spread across the planet, Billions of people from every nation participated in an unprecedented global referendum. The debate raged for weeks, passionate and profound, touching on every aspect of what it meant to be human and what we owe to the memory of another civilization. The vote was close but decisive, 58% in favor of rescue. The recovered Atlas probe sat in a specially constructed facility at the International Space Station, its systems dormant but stable, its archive intact. Teams of scientists from every nation worked in rotating shifts, carefully documenting and translating the vast repository of knowledge it contained. Dr. Chen stood before the ancient vessel, running her hand along its ice-scarred hull. Inside was everything, the hopes, dreams, achievements, and failures of an entire species. They had sent this message in a bottle across the vast ocean of space, never knowing if anyone would find it, never knowing if they would care. "What do you think they would have wanted?" asked Morrison, standing beside her. Chung considered the question, thinking of the binary message that had changed everything. Request, assistance. "I think," she said slowly, "they wanted exactly what they got. To be heard, to be remembered, to know that someone, somewhere would care enough to try." Outside the station's windows, Earth turned slowly in the darkness, a blue marble in the infinite void. And for the first time in its history, humanity knew with absolute certainty that it was not alone, and had never been alone. The universe was vast and ancient, and filled with voices calling across the darkness. Atlas had been just the first we'd learned to hear. The question now was, what would we say in return?